Hello class, this is Dr. Ben. I'd like to take a few minutes to work on a practice problem that has to do with projectile motion that's in the last part of chapter 4. So we have the situation where a rock is thrown from some initial position and we're given its initial velocity components, and we're asked to find the velocity components 1 second after the rock reaches the top of its flight. And we're supposed to ignore air resistance. So let's draw a pictorial representation for this problem. So we'll put it on an ordinary XY coordinate system. And let's pick the initial position of the rock to be at the origin. And if we kind of trace out the trajectory that we expect, one of the points of interest that we're told is at the top. And we know that at that point the velocity in the y direction is equal to 0. It's the turning point. And then the problem asks us to find out the velocity components of the rock 1 second after it reaches the top. So that's going to be a point that's further down the trajectory. So let's label these points 1, points 2, and point 3. And we can write the acceleration that influences the rock. The acceleration in the y direction is going to be minus g in this coordinate system. So we can go ahead and make a table of what we know and what it is we want to find. So we're given the initial velocity components, v1x equals 20 meters per second, and v1y is equal to 30. We have the approximate value of g, 10 meters per second squared, and the time interval between points 3 and points 2 is given to be 1 second. And point 2 is at the top, because the y velocity at point 2 is going to be equal to 0. Alright, so we want to find the value of the velocity components at point 3, v3x and v3y. Alright, so we know that in projectile motion, the x direction, the motion is uniform. So that means there's nothing to change the velocity in the x direction, and so v3x, there we go, should be equal to v1x, and that's going to be the value that was given, that was the 20 meters per second. So the x velocity always remains the same in projectile motion, and that's actually part of the model that we use to solve the problem. But in the y direction, the velocity changes because it's accelerated, and acceleration is down, and so we recognize the pattern in projectile motion that objects slow down as they rise and then they speed up as they fall. And even though we can use the kinematic equations in the y direction for solving this problem, we can actually just reason out the answer using the definition of acceleration. So to remind ourselves, acceleration is equal to delta v delta t, and I would be interested in applying this in the y direction. So, for example, if we would consider the numbers for this case, that the acceleration is equal to negative 10 meters per second squared, that would be equal to the change in velocity. And if we just consider, for example, that we consider a time interval of 1 second, then the change in velocity that's going to occur over that time interval will be equal to negative 10 meters per second. So the y velocity is going to gradually decrease until it becomes 0, and then it will increase as it comes back down. And since we know that the initial velocity in the y direction was actually equal to 30 meters per second, we can use this fact that we know the acceleration to count forward in time to find out how many seconds it takes for the object to get to the top, and then 1 second more to get to point 3. So the velocity in the y direction is going to decrease by 10 meters per second every second. So if we start out with 30, then after 1 second of time, the velocity should have decreased to 20. And then after another second of time, it should decrease by 10 meters per second more to get to 10. And then finally, in 1 more second of time, the velocity would become 0. So if this is time 0 seconds, 1 second, 2 seconds, and 3 seconds, we've established that the time that is at the top of our trajectory is going to be 3 seconds after the experiment started, and therefore the time at point 3 that we're really interested in is going to be 4 seconds of time. So the velocity decreases in the y direction at a steady rate of 10 meters per second per second. So it takes 3 seconds of time for the velocity to decrease from 30 to 0. And then on the way back down, we would have 0 meters per second at 3 seconds, and now the velocity would become more negative, and it would go to negative 10 meters per second at the end of the 4th second, because it would speed up, but the velocity is downwards. And so at the end of the 4th second of time, the value of the velocity in the y direction is going to be equal to negative 10 meters per second. All right, so we've answered the question that we were aiming for. We found the value of the x velocity remained constant because we had uniform motion. We found the value of the y velocity at this point of interest. We had to figure out what was the time associated with this third point, and we did that by finding out the time for the top. And so just to finish up, we'll double check that we have our units. Both of the components have meters per second. Our significant figures look good.